Welcome to Study Loop.
19.95. So we have a radio tuning capacitor. Older radios did their tuning. Newer ones have other ways of getting a variable capacitance that doesn't involve a somewhat bulky mechanical assembly. And so it consists of one set of these little plates that can rotate with respect to some axis that's shared with these other plates. And so the sort of area of overlap can be varied. And we know that the capacitance of a capacitor depends on the area of the plates. So we can vary that, so we can vary the capacitance. And each of the plates has a separation from its neighbor of 1.6 millimeters. And so first we want to ask whether it's in series or parallel. And for this sort of thing, it can be helpful to it can be a little confusing thinking about the problem just states that there are 7 capacitors here. And even just figuring out how many capacitors there are, it can be a little bit tricky if you aren't used to thinking about these things. So if we think of each of the little plates here as having some thickness, they're not meshing very much here, but whatever. All of these are connected together. All of these are connected together. Either side of one of these plates acts as sort of an independent plate in a capacitor formed with an adjacent plate. So this pair of surfaces forms one capacitor, and this pair of surfaces forms another, and this pair of surfaces, and that pair of surfaces, and so on. And so you have positive charge on one side of this and negative charge on the other. Or it's all positive charge in this case. But there's positive charge on one side and positive charge on the other, and so that acts as 2 separate capacitor plates that are just connected together. And so we can see we have 1, 2, 3, 4, 5, 6, 7 of these little lines showing the connections between our plates, or the gaps between the plates, whatever. And it's clear that all of these plates are at the same potential, and all of these plates are at the same potential. And so each of our capacitors here has the same potential difference across it. And so they're all in parallel. Now to find the range of capacitance values, we have 7 capacitors in parallel, and the capacitors are all identical. And so this is going to be 7 times the capacitance of one capacitor here. And we know that the capacitance of a parallel plate capacitor is epsilon naught times the area divided by the separation. So the minimum capacitance is going to just be one with the minimum area. So we have 7 epsilon naught A min, which we see is 2 square centimeters, divided by D, which is the same in all cases, for 1.6 millimeters. Now it's important to convert square centimeters and millimeters to square meters and meters respectively in order for this to work out. Or because it ends up being dimensionless, you could just convert this to square millimeters or this to centimeters. Actually, converting this to centimeters would be the easiest. Because then you have square centimeters divided by centimeters, and the conversion factors for meters should cancel. Oh wait, no, you'd still have one factor of the conversion factor per centimeters left. Um, so it's better to actually no, it's better to just convert them both to meters. I thought I could be clever there. Anyway, if you do it correctly, um, and if you think you see some sort of time-saving trick, make sure to think it through all the way, like I did just there. You get 7.7 times 10 to the negative 12 farads is our minimum capacitance. This is 7.7 picofarads. And the maximum capacitance is similarly going to have our 9 square centimeters, which is just discovered should be converted to just be converted to square meters to minimize the amount of potential confusion. And that gives us 3.5 times 10 to the negative 11th farads. Which is 35 picofarads.